In this video, we get to see limiting behavior in Markov chains. If you follow, I have a playlist on calculus, right? And before you get deeply into calculus, you start looking at functions, types of functions, graphs of functions, and at some point you begin to consider the limits and continuity of functions. So just like in functions, when we come to stochastic processes like Markov chains, we get to also observe some limiting behavior in them. So that's what this video is about. So limiting behavior in Markov chains. And the first thing we want to ask ourselves is, what is limiting behavior? So a Markov chain describes a system that transitions between states with fixed probabilities. So like we've seen already, if today is rainy, what's the probability that tomorrow is going to be rainy too, or sunny or cloudy or anything like that? That is a Markov chain. So the limiting behavior answers this question. What happens as the number of steps becomes very large? So as you keep, moving from one state to another, what tends to happen at equilibrium, so to speak? Mathematically speaking, we have the limit of p raised to power n as n approaches infinity. That is probability. So as the number of steps you take in a stochastic process, or especially in specifically a Markov chain, so as the number of steps becomes larger and larger, what is happening at the end of the day, right? So I guess this even needs some uh uh something like this to make it stand out. Yeah. Yeah, just italicization there. So P is the transition matrix, right? And Pn represents the system after n steps. Okay. So then we go on to talk about the transition matrix, which we have considered in previous videos, right? So here a transition matrix P is defined by Pij, which is equal to P of xn plus 1 equals j, given that xn is already I. So the question is like, what is the probability of moving to j, given that you are coming from I, right? Or what is the probability that you are going to get to j tomorrow, if today is already I? So in this case now, each row sums to 1, all right? I mean, we've seen what we've looked at transition matrices, and we already understand this concept. And the fact is that every entry in a transition matrix is non-negative, right? And it is less than 1. And then every row sums up to 1. Very important. And then we have what we call the state distribution. That's the probability vector, which evolves as pi raised to power the number of steps is equal to the initial state multiplied by the transition matrix raised to power the number of steps. So, and then that takes us to the idea of stationary distribution. I have a video on one of the previous videos was of stationary distribution, where we looked intently into this whole idea of the equilibrium state of a Markov chain. So a stationary distribution pi satisfies pi p equals pi. This represents the long run equilibrium. So it's like some kind of steady state of a Markov chain. So 22.5, we then see this idea of types of limiting behavior. First of all, we have convergence to a stationary condition. So a Markov chain can converge to a stationary distribution. I remember one of the previous problems I solved, where you have like an absorbing state in a matrix. That is in one of the rules, you have one of the items to be one of the probabilities to be 1, meaning that every other probability is 0. So that probability of 1 means it's an absorbing state. And as a result of that, you do have a convergence to a stationary distribution, because that is absorbing behavior, as you see in number 3. Then in between that, you have periodic behavior, which is oscillation. That means like after every fixed number of steps, you come back to where you started out from. So we also saw examples of that in the previous video. We are going to see that again here. So yeah, there are 3 types of limiting behavior we're talking about. There's convergence to a stationary distribution. You can have a periodic behavior, which is oscillation. That is, you take a number of steps and you come back to where you started from, and that keeps going on like that. And then you have absorbing behavior. One key way to identify absorbing behavior is that one of the probabilities in the transition matrix is 1. So any state where you have that 1, that means that state is an absorbing state. So that's absorbing behavior, which is a type of limiting behavior. So you have convergence, periodic behavior, and absorbing behavior. So talking about convergence conditions now, a Markov chain converges if it is irreducible, that is, all states communicate, and then it is aperiodic. Now, all states communicate means that there's no state absorbing, there's no absorbing state, you know. all states communicate. So then it is aperiodic. That is, it does not come back to the original state after some moves, right? So this basically convergence precludes periodic behavior and absorbing behavior. So convergence only happens if there's no periodicity and absorbing behavior. Then we say that the limit p power n as n approaches infinity is equal to pi 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 pi. So you now have a steady value going on there. So we have a very good example of this now. For basic convergence now, imagine you have p probability, the probability matrix is 0 0.7, 0 0.3, 0 0.4, 0 0.6. And you say let pi be pi 1 and pi 2. Because for convergence, we need to we'll get proper pi for pi p equals pi, right? And if pi 1 and pi 2 are pi, then we can say that. So it's more like we're saying we have, okay, let me see what that is again. Okay, you know what? I'll do what I usually do. I'll just run through it and then I'll go over to the worksheet and work it out in case you need some clarity on that. So for basic convergence here now, consider P. So you can see there's no absorbing state already. There's no one anywhere. So that means there's no absorbing states. Both states are communicating, right? So you can move from state 1 to 2 or from 2 to 1. That's what it means that the states are communicating like that. So so let pi be pi 1, pi 2. So pi p equals pi. This gives 0 0.7 pi 1 plus 0 0.4 pi 2 equals pi 1. And of course, we have this normalization that pi 1 plus pi 2 must always be equal to 1. And if you do all that, you get pi 1 to be 4 over 7 and pi 2 to be 3 over 7. So let me go, and a lot of steps have been jumped here. So I'll just go and do this. 0 0.7, 0 0.4 is the transition probability. So p is 0 0.7 this, then 0 0.4 this. Of course, the reason why I just try to memorize just the first two, this and this, is I already know that whatever you have there, any other thing you're going to have must add up to 1. And that's why with that in place, I know that if this is 0 0.4, this is automatically 0 0.3. If this is 0 0.7, this is automatically 0 0.3. If this is 0 0.4, this is 0 0.6, like that. So that's what we have there. So now we want to find the convergence. So to investigate the uh convergence, so to speak, to investigate the convergence, we find we find pi such that pi p is equal to pi. And because our transition matrix is a 2 by 2 matrix, what do? We need pi. So we can say since P is a 2 by 2 matrix, all right, then pi should be a a 2 by 1 row vector, a 1 by 2 row vector. That's pi 1, pi 2, like this. So that way now, therefore, we have pi p equals pi to be, so pi p now is pi 1, pi 2. So this is now 0 0.7, 0 0.3. Then this is 0 0.4, 0 0.6, and that is equal to pi 1, pi 2, like that. So we then have so pi 1, pi 2, and yeah, and we multiply out. So this is only one row. So it means we're going to write each row once, each of these columns rather once. So we have 0 0.7, 0 0.7, 0 0.4 multiplied by pi 1, pi 2, and the other one 0 0.3, 0 0.6 multiplied by pi 1, pi 2, like this, and this is equal to pi 1, pi 2, like that. So then we have 0 0.7 pi 1. So this is 0 0.7. I intended to change this. So this is 0 0.7 pi 1 plus 0 0.4 pi 2, and this is 0 0.3 pi 1 plus 0 0.6 pi 2, and that is equal to pi 1, pi 2, like that. So in this case now, we can then equate both sides, right? So first we have 0.7 pi 1 plus 0.4 pi 2 equals pi 1. So this whole thing is equal to this. So, and this is pi 1 here. So it means that we can have 0.4 pi 2 equals pi 1 minus 0.7 pi 1. So this is 0.4 pi 2 equals 0.3 pi 1. So this is what this has reduced to, right? This is what this would reduce to. So before I come back to that, I also want to look at the other side of it, the other part. That is, this equals this now. Okay, so that's 0.3 pi 1 plus 0.6 pi 2 equals pi 2. So that means you have 0.3 pi 1 plus 0.3 pi 1 is equal to pi 2 minus 0.6 pi 2. So that means you have 0.3 pi 1 equals 0.4 pi 2. So you see that these two are just similar, they are the same in essence. So it means you just pick one of them and keep moving, right? So generally we have 0.3 pi 1 equals 0.4 pi 2. And then we recall that one of the conditions here is that pi 1 plus pi 2 should be equal to 1. Okay, if that is the case, we then have that 0.3 pi 1 will be equal to 0.4 pi 2. All right, so this implies that pi 2 is equal to 1 minus pi 1. Okay, so instead of having 0.4 pi 2, this is 0.4 into 1 minus pi 1. So this is 0.3 pi 1 equals 0.4 minus 0.4 pi 1. Okay, so we put things together. We have 0.3 pi 1 plus 0.4 pi 1, and that is equal to 0.4. So this is 0.7 pi 1 equals 0.4, like that. So that we then have pi 1, divide both sides by 0.7. So you have 0.7 equals 0.4 divided by 0.7. So this cancels out, so that pi 1 becomes, 0.4 over 0.7 is simply 4 over 7. So with this in place now, we can then say from we have pi 1 now, right? We have pi 1 now. So from pi 2 equals 1 minus pi 1, right? We have pi 2 to be 1 minus 4 over 7, which is simply, well, if you want to be finicky, that's pi 2, which is 1 over 1 minus 4 over 7. So that pi 2 is equal to LCM is 7. 1 is 7 is 7, minus 7 is 7, 1. 7 is 7, 1. 1 times 4 is 4. So that pi 2 is equal to 3 over 7. And we have that overall. So pi, which is pi 1, pi 2, is equal to 4 over 7, 3 over 7. And that's exactly what we have on that page there. Okay, that's what we have back here. So pi 1 is 4 over 7, pi 2 is 3 over 7. So by the way, 4 over 7 is 0.57. Okay, well, I can demonstrate that, right? So we have if you run the code you have 0.571428 blah blah blah, like that. So if I create a new cell and I just want to print say 4 over 7, 4 over 7, comma 3 over 7, 3 divided by 7. Okay, so it's exactly the same value. So that's what it is. So if you do the code you get the same thing. So you see, this is pi I equals pi multiplied by p. So we see that the distribution converges to 0.57, 0.4286, which matches 4 over 7, 3 over 7. So that means that at the end of the day, the possibility, so at equilibrium, right, there's a higher chance of reaching state 1 than reaching state 2, but there's no absorbing situation actually. So we can do the matrix power approach too. So in this case now we compute p raised power n, All right. So like any number of steps you want to take. So as the steps increase, it gets bigger and bigger, then you see how these things go. For instance, okay, you have P10 to be, maybe we can start gradually, right? Maybe okay, what I'm just going to do is I'll just keep changing the values. So let's start with P1, that's just one step. That's the beginning of everything. So it's referring to this matrix P, this same matrix P, 0.7, 0.3, 0.4, 0.6. So that you should expect that at P1, right? So you see 0.7, 0.3, 0.4, 0.6. That's what we have first. So what if you now go second step, P2, that's you raise the matrix to power 2. So now we want to see what P2 looks like. So you see now it has moved. It's now 0.61, 0.39, 0.5 to 0.48. Now, then we go the third step. Okay, we take the matrix to third step, and then we have to see V3 here. So for this V3, we have 0.583, 0.417, 0.5. So things are still changing for now. Okay, you know what I'm going to do? I'm just going to keep changing only the power alone so that we don't have a problem. So let me just call it Pn, and then call this Pn. Whatever I put n is, I'll come back later and change it to 10 that way I had there before. So I just keep, so this is step 3 now. Step 3 is 0.58. So what about step 4? 4. So for step 4, 0.5749 and all of that. Then step 5, we're 0.5724. So it's still changing, right? Step 6, or maybe step 5, right? You have 0.5714, 0.42. So things are beginning to look uh, close by. So 0.57, okay. Step 8, 0.5714. Step 9, 0.57, blah, blah, blah. Step 10, step 11. So as you keep going, what about step, let's jump now from 11, let's jump to step 20. So you see the value keeps hovering around the same thing. It starts changing gradually, and it gets to a point it tends to stabilize. What about step 200, right? It's still the same value, so things are getting clearer. So it's basically the two of them are getting exactly the same thing now. So 0.5714, 0.4285, blah blah blah. So let me go step 2000 and stop there. So you see nothing much has changed. So this tells you that's the steady state of this system. So like that. So let me go back to 10. So you can see 10 doesn't look too different from what we have even at 2000. So that means that the system has reached some kind of equilibrium. So we now see that here that all rows are identical because and that indicates convergence, indicates convergence. So you have 0.571, 0.571, 0.429, 0.429, like that. So we can also have a periodic chain. So for a periodic chain, right, uh this system alternates between states, right? So as you keep going, you come back to where you started from initially. So imagine this transition probability. So of course, for this periodic chain, you have the two states are absorbing, right? In fact, there's like no movement. This system alternates between states. So you have P0110 like that. So you declare that here as an array, and then for n in range 1, 1, 6. So this is 6, right? We're even going, this is 6 indicates 5 steps. So when we start from the original, which is yeah, when we start from the original, that's 0, right? That's the initial state. Okay, this is not giving us anything. So because okay, p raised by 0 is 1. So if I make it state 1, okay, nothing. So first step now, that's 2 right there. First step, you see, first steps gives exactly the same thing. 0, 1, 1, 0. Nothing has changed. Because moving from 1 to 2 means 1 to 1, basically. So that's for a Python thing now. So this is like step 2. So step 2, if I run this, you have step 1, 0, 1, 1, 0. And then step 2 is different. It's now 1, 0, 0, 1. But guess what? In step 3, well, if I declare this to be 4, in step 3, we come back to where we started from. So after every 2 steps, we come back to the original. So this is different. We come back. Then if I go step 4 now by putting 5 here, all right, we have a different result. We have something like this again. And then at step 6, if I put 6 here, that's step 5. So that's another 2 steps. We come back to the same thing we started from, like that. So and that keeps going like that. That's periodicity, that after every two steps you come back home, something like that. So we observe that p squared is I. So you see p squared is equal to I is the identity matrix 1001, whereas p cube is p, the p you started with. So we have that kind of thing. So every even power of p takes us back to gives us the identity matrix, while every odd power of p gives us the original p we started with. So the system then oscillates and does not converge. That's what that implies. And then when we talk about absorbing chain now, so now, if you look at the periodic situation, right? In the periodic situation, the two states are absorbing, right? But then in the absorbing chain, only one state. If all the states are absorbing, you are likely going to have periodicity. But if for an absorbing chain you have one state is absorbing, the other is not, then you can think about an absorbing chain in that sense. So you have P to be 1, 0, 0.3, 0.7. So here, state 1 is absorbing, but as you go over time, what happens here? So you discover that that state 1, that state 1, state 2 also tends to have the same absorbing nature as you keep going and going. So let's start from something very small. Let's start from, as usual, let's start from our 0 now. Okay, of course, that's 1001. But what if we start with 1? So if you go for 1, we have 100, 0.3, 0.7, like that. That 1001 we got before. That's one in matrix terms is unit matrix, right? So here, P1, you have this. So what about P2? So you have 10, 0.3. So the first one is the absorbing state. So if you go to, okay, things are beginning to change. So this one is increasing while this is decreasing. We go step 3, all right, and we have, okay, you can see this is still increasing and this is reducing. So it's more like this row is converging towards the absorbing state too. So at the end of the day, we are going to have that absorbing kind of situation. So if I go 4, see what happens. So this is increasing and this is still reducing. So if I go 5 and do this is 0.83, this is 0.16, really increasing. If I go step 6, if I go power 6, right? So this is still increasing. 7, still increasing. 8 now, still increasing. So this is fast moving towards 1, while this is fast moving towards 0. Then 9, okay, 9, still increasing. So I go 10, 10, still increasing. So let me go to 20. Let me jump to 20 here. Okay, now you see this is 1 now, and this is almost 1. In fact, this is 0.999. What if I go 30? 30, and this is 0, right? This is 0.000 something. So it's really small now. Okay, it's going to 30, it's getting even closer. All the nines are increasing. Let me go to 100 then. So if I go to 100, what do we have? So you see, this is 1 decisively. This is also 1 decisively. This is 0. Now, this is as good as 0 because this is 3.2 something times 10 raised to the power minus 6. That's 15 zeros before you get to the number. So this is as good as 0. So at the end of the day, we see here that for this absorbing state, the limit of p power n as n approaches infinity is 1010. In this case, all probability ends in the absorbing state, like that. All probabilities end in the absorbing state. So we also have an eigenvalue perspective to the limiting behavior in Markov processes. If eigenvalue satisfies that lambda 1 is 1 and absolute value of lambda 2 is less than 1, then we say that Pn implies a rank 1 matrix. So if one of the eigenvalues is 1 and the other one is less than 1, the absolute value of the other eigenvalue is less than 1, then we have a rank 1 matrix, just like in this case now. So for this P, the P we started with, right? This particular 0.3, 0.7. So the eigenvalue at the end of the day gives us this. Of course, if you are wondering what eigenvalue is, you may want to check my playlist on matrices, on on dynamical systems and all that. So we talked about eigenvalues a lot, even in linear and abstract algebra, especially linear algebra. So you want to check that out if in case you wonder what eigenvalues are, like that. Okay. So in summary, we have this that if you have So talking about case and behavior, if you have an irreducible and aperiodic case, the behavior converges. Then if you have a periodic case, you have oscillation. If you have an absorbing case, it ends in absorbing state. Then if you have something that is reducible, then that depends on the structure. Okay, so the final intuition we get here is that a Markov chain behaves like a random process that eventually settles into equilibrium. That's one possibility. Another one is that it cycles forever. That's that periodicity that after two steps, it comes back to the original thing. Or you can have another one that after three steps, it comes back, or after 10 steps. It all depends. Then it can also get trapped. So that talks about convergence, periodicity, and of course, absorbing behavior, depending on the structure of the probability, the transition matrix. So we have practice problems as usual. I mean, I've talked about this a lot, so I may not even need to do anything here. So given this, now find the stationary distribution. Of course, you already know that's pi p equals pi. Then for problem two, determine whether the chain is irreducible and aperiodic. So here you want to check periodicity. So if you, I mean, I believe this is periodic actually. So after two steps, it's this the same matrix we dealt with the other time. Then compute P5, you can use the linear algebra thing I did the other time. So compute this. We've done this type of thing. You want to check that out too. Discover, does the following chain converge? I think it's simply periodic, right? Then finding the limiting matrix. Okay, so you want to find the limiting matrix here. So you just it's more like you're looking for pi still. Is the chain absorbing? Absolutely, because you have one here. So it's once you see one in any state, in state one is absorbing. So compute eigenvalues of this. Okay, maybe I want to do this for those who may not understand the idea of eigenvalues. So P is you have 0.7, 0.3. Okay, I mean 0.7, 0.2. So um to compute to compute the eigenvalues of P, which is 0.7, 0.2, that's 0.7, 0.3, and 0.2, 0.8. So generally speaking, okay, generally, the eigenvalue lambda, the eigenvalue lambda can be obtained from the integral of of p minus lambda I. Notice the eigenvalue now, and this absolute value is equal to 0. So that means that our p now, which is 0.7, 0.2, right? So we have 0.7, 0.2, then 0.3, 0.8 minus lambda into the uh, identity matrix. That since it is 2 by 2, we have 1, 0, 0, 1. This determinant is equal to 0. That's how we find eigenvalues, right? So in that case now, we then have this to be 0.7, 0.3, 0.2, 0.8 minus lambda 0, 0 lambda equals 0 like that. And then this is equal to 0.7 minus lambda 0.3 here, 0.2, then 0.8 minus lambda, and that is equal to 0. Okay, so having done this now, we can move on to say that this is now to find the determinant here, right? You have 0.7 minus lambda, so you multiply this and this, right, and subtract that. So 0.7 minus lambda into 0.8 minus lambda minus 0.3 times 0.2, all of this is equal to 0. So we multiply things out. We have 0.7 times 0.8, that is 0.56. Then 0.7 minus lambda, that's 0.7 lambda. Then minus lambda minus 0.8, that's minus 0.8 lambda. Minus and minus is plus lambda squared. Then minus 0.3 times 0.2, that's 0.06, yeah, equals 0. So we tidy things up. So here now we have lambda squared, then minus 1.5 lambda, this is minus 0.7 minus 0.8. Then 0.56 minus 0.06, that will be plus 0.5 plus 0.5, that's all we have there. Yeah. And that is equal to 0. So what do we do here? We can actually multiply through by 10. Is that necessary? So if we multiply through by 10, yeah, if we multiply through by 10, we get 10 lambda squared minus 15 lambda plus 5 equals 0. Okay? 10 lambda squared. So 1.5 times 10 is 15. Then we can then divide through by 5. So that is 2 lambda squared minus 3 lambda plus 1 equals 0. Okay, now it's easier to handle this. So solve now. To solve this, we need two numbers, right? We need two numbers. When multiplied, we get 2 times 1. That's 2. Then with the same two numbers, when added, we get minus 3. And usually, those two numbers will be factors of 2. So we know that should be 2 and 1. And because we need minus 3 here, this number should be minus 2 and minus 1. Minus 2 and minus 1 is 2. Then minus 2 minus 1 is minus 3. So we got our factors easily like that. So we then go ahead to have 2 lambda squared minus, so for minus 3 now, that's minus 2 lambda minus lambda, that's minus 1 lambda, right? Plus 1 equal 0 is equal to 0. So we have 2 lambda squared minus 2 lambda, all right? We group minus lambda minus 1 equals 0. So we then have, we factorize now. So 2 lambda is common. So you have 2 lambda into lambda minus 1 minus 1 into lambda minus 1 is equal to 0. So we have that we factor out this now. We factor out lambda minus 1, lambda minus 1. So this is lambda minus 1 into 2 lambda minus 1, and that is equal to 0. Okay, so from here now we then say lambda minus 1 equals 0, or 2 lambda minus 1 is equal to 0. So lambda is equal to 1, or 2 lambda is equal to 1. That means that lambda is equal to 1 over 2. And then you see now that lambda is 1, and or lambda is 1 over 2. And there was a rule the other time that the absolute value of lambda here now, is equal to 1. I mean, the absolute value of lambda is equal to 1. So, I mean, the absolute value of lambda is less than 1. And we have a condition attached to that, which we saw previously, that if one lambda is 1 and the absolute value of the other is less than 1, then we say that Pn is a rank 1 matrix, okay? So Pn is a rank 1 matrix. Okay, so so since lambda 1 is equal to 1 and the absolute value of lambda 2 is less than, should I just write it out so we can see the absolute value of lambda 2, the second lambda, okay, is equal to half, which is less than 1, right? Then we say the transition matrix after n steps is a rank 1 matrix. So that's what we have for that. Okay, so you want to try your hands on the other questions as much as possible. So that was that question involving eigenvalues. Okay, where is that now? Determining the chain is reducible. Find stationary distribution. Of course, that's by n and all that. Check periodicity. So if you keep raising it to increasing the steps, you see if it comes back to a point you started with later, that's periodic and all that. So try your hands on the rest of these things and let's see how well you understand them. So again, I tried to flash the questions. So this is 1 to 3. Then you have 4 to 6. You have 7 to 9. You have 10 to 12. You have 13 to 15. you have 16 to 18, you have 19 and 20, right? So try your hands on them and let's see how that goes. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed already, I thank you very much for doing that. If you haven't subscribed, why not go ahead, subscribe, hit the notification bell so you can always get alerted each time a new video is released. If you also want to go further, you can become a member of the channel by clicking on join, which gives you special privileges like getting to see some videos first or seeing some videos exclusively as a member of the channel. You can also request for PDF copies of my notes. We can hang out together to discuss whatever interests you on this channel also. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.